Now, let us look at what is called a current divider circuit. Simply, what we have is a current source that is connected to two resistances R1 and R2. And R1 and R2 are in parallel, right? R1 and R2 are in parallel. So in other words, what you can do is to replace this guy, the two resistances, with one equivalent resistance, R equivalent, with everything else unchanged in this circuit. Okay, now the equivalent resistance R equivalent is R1 times R2 by R1 plus R2. Remember, the resistances are in parallel, right? R1 and R2 are in parallel. So the equivalent resistance, so in other words, both of these circuits behave exactly the same at these terminals, right? So the terminal behavior of these two circuits with respect to these two terminals is exactly the same. Okay, so that's R equivalent. Okay, now let's see, what are we interested in finding out? Remember, this is a current divider circuit. What really is happening is the current I source that is being supplied by the current source, this current source supplies a current IS. Okay, what is happening is that is being split at that node. Okay, remember, there is a current coming in IS and it has to branch into two paths. Okay, so I'm going to call this current I1 and this current I2. Okay, so the total current IS is being split or divided between two branches. Okay, hence the name current divider. Now we are interested in finding out I1, I2. Okay, pretty straightforward. Now, the one thing that we want to bear in mind is the resistance R1, the resistance R2, and the current source, they are all in parallel, right? All the three circuit elements are in parallel. Therefore, the voltage across all of those is the same. Okay, so that's the fundamental property of elements that are in parallel. The voltage dropped across those is the same. So I'm going to call them little v. Okay, so the voltage across the voltage source is the same as the voltage dropped across the resistance R1, which is V1, which is the same as the voltage dropped across R2, which I'm calling it as V. Okay, which I'm calling as V. Now, we are interested in finding out I1 and I2. So remember, the voltage dropped across R1, that's the voltage drop, right? It's same as V. V is, using Ohm's law, I1 times R1. Okay, and also that's the same voltage that is dropped across the resistance R2 as well. So Ohm's law, I2 times R2 is the voltage dropped across the resistance R2 as well. Okay, now what we can do is we can see what values we can plug in place of V. Okay, if you think about it, I earlier drew the equivalent resistance, right? There is one current source which is driving an equivalent resistance, R equivalent. okay, because this represents the parallel R1 in parallel with R2, okay. So the R equivalent is going to be given by that formula, okay. The current Vs, the current Is sets up a voltage V across this equivalent resistance. So you can calculate V, right? You can express V to be Is times R equivalent, okay. That's the same voltage that is dropped across the resistance R1. That's the same voltage that's dropped across resistance R2. So all of these voltages are really the same. So all I have done is to express V in terms of the current source and the resistances R1 and R2. Okay, let's see if we can use these results. Okay, so in place of V over here and over here, I'm going to replace it with Is times R equivalent. Okay, let's see. So let's start with this equation first. Okay, I'm going to copy that or even duplicate it. Okay, and then in place of V, I'm simply going to replace it with I equivalent times Is times R equivalent. So simply put, Is times R equivalent is I1 times R1. Okay, why are we doing this? Because remember, we started out by saying that we want to get an expression for I1. We want to find I1. Therefore, I1 really is Is by R1 times R equivalent. Okay, and we remember what R equivalent is. R equivalent is R1 times R2 by R1 plus R2. Because they're in parallel, we wrote out the equation R equivalent from here, right? R equivalent is R1 R2 by R1 plus R2. Okay, that's all I have done. So you can see, therefore, that I1 is R1 cancels out, R2 by R1 plus R2 times Is. Okay, this is an important result when it comes to current division. Okay, now you can also show that I2 is R1 by R1 plus R2 times Is. Okay, now if you think about it, the relationship between the resistances and the currents is not direct. You will see that the larger resistance has a smaller current and the smaller resistance has a larger current. So here is this is the notion of current division, right? Okay, so if you go back, we started out with this circuit. We wanted to find out the expression for I1 and I2, right? And I mentioned that I1 is R2 over R1 plus R2 times Is, right? Similarly, I2 is R1 by R1 plus R2 times Is. Okay, so that's the idea. The total current Is is divided between R1 and R2. Okay? So before we leave, let me give you a quick analogy. Okay? A quick analogy that we can relate to real world. Think of resistances as speed bumps, stoplights, traffic signals. Okay? And current, think of the current as the traffic. Number of cars. Okay? Let's say there are two roads. One road has a number of stoplights, a number of speed bumps, and a number of stop signs. Okay? And let's say the other road has fewer stoplights, and it's a pretty easy breeze, a path. Okay? Intuitively speaking, which road do you think has more traffic? Obviously, the green road, because it has very little resistance to traffic flow. Similarly, if a resistance is big, it has lower traffic or lower current, and if a resistance is small, then that has higher current. Okay? You see the idea? The lower resistance has higher current, and the higher resistance has lower current when they are connected in parallel. That's the idea of current divider. Okay? And we will illustrate this using an example problem.